Hi everyone, this is Mr. Lee. In this video, we are going to go over rotational inertia. Let's begin. Let's formally define inertia. We didn't really do this back in Unit 2 with forces, but inertia, which we represent with the variable m, is how much the object resists changes in motion. And you'll see that I highlighted two different parts because even though we describe inertia as m, which is mass, and we can see object, right? We usually say object is m. Inertia itself is a two-part component, okay? And if you're thinking ahead, changes in motion is what we essentially call acceleration. So you can see already right here how much the object resists changes in motion. And you can see your two variables are m and a. If my question is, what causes that change in motion? Hopefully you are all saying right now, well, of course, Mr. Lee, it has to be force. And that's where we get Newton's second law. So let's describe inertia using this example. Let's say you exert a force of 100 newtons on two different objects. So I'm going to write out that formula. So if we're using Newton's second law, F equals ma, let's say in scenario one, we have big inertia, all right? And in scenario two, we have small inertia. So the important thing that we want to focus on is this, the changes in motion. It's the acceleration that tells you if your object has a lot of inertia or little inertia, as long as you're applying the same force. So if we have F equals ma here, all right, if we have a force that is equal for both, but the inertia is big, we're going to make this nice and big, that means that the object will accelerate less. Okay, compared to over here, F equals ma, if we have the same force that's applied, okay, but the inertia is small, that means when you exert that force, it's going to have a big acceleration, right? And if I were to use layman's terms, if an object has a big inertia, okay, it's going to speed up slash slow down more than if an object has like less inertia, okay? Or maybe I flip that, but the idea is there. All right. Now, what about rotational inertia? So, rotational inertia is essentially the same thing. It's how much an object resists changes in rotational motion. So before we go into the formal definition and the formula, I want you to think of this. So let's say you have like a giant wheel, right? Like a monster truck wheel. And so we'll have two different scenarios. In scenario one, this monster truck wheel is made out of, I don't know, concrete or like steel, something with like a lot of, oomph behind it. So that compared to in scenario two, same size monster truck wheel, but for whatever reason, the engineers decided to use light styrofoam, right? So we can say, if I were to ask you, in which scenario would it be easier to stop this wheel coming right at you, right? It will be easier to stop the styrofoam wheel because it has less rotational inertia compared to the concrete wheel. Now, let's look at the vice versa. If I were to ask you, in which scenario would it be easier to get that wheel to start spinning, right, which is the opposite definition here of the acceleration from the previous example, you would say, Mr. Lee, same answer. It is easier to get the styrofoam wheel to start spinning compared to the big concrete wheel. All right. So you have to think about inertia in two ways, right? But both dealing with acceleration, where it's like speeding up and slowing down. Okay. So with that being said, let's come up with the formal, I guess, idea slash formula for rotational inertia. By the way, rotational inertia, the variable is I. All right. Now, before I give you the formula, I need you to know where this formula comes from. So let's say we have a particle, all right? And this particle is spinning around in a circle, okay? And it's spinning around with constant velocity. And this velocity is tangential in nature, so it has VT. Now, this might look really familiar, right? So this is basically centripetal motion. So if this particle is spinning around and around and around, okay, what you're looking at is the idea of rotational inertia. So if I were to ask you, all right, so let's say this particle that's spinning around and around and around, it's made out of, let's go back to like lead or steel, something very like oomph, right? Very dense. that would have a lot of inertia. So, meaning it would be harder to get that particle to spin faster or slower. Another way you could think about this is let's say you have a brick in your hand versus a styrofoam ball in your other hand. If I were to ask you, which one is easier to spin around your body like this, like going back and forth? Of course, a brick will be more difficult. So, one of the variables for rotational inertia, using this idea of how hard is it to get it to speed up or slow down, okay, is the variable m. And you've probably seen that coming from a mile away. Now, because we're in the rotational unit, the other idea of, or the other variable that's important here is the radius, but the way that the calculations work out is that the radius is in fact squared. Now, this is for a point particle. So it's the most basic formula for rotational inertia. And by that, what I mean is that different objects that are rotating have a different rotational inertia formula. And if you want to become an engineer or go into more advanced things, right, there's actually a chart that tells you the rotational inertia for different situations. I'm going to show you that chart. This is a very basic chart, but the important thing that I want you to see is that the m and the r will always be there, and it will be always m and then r squared. All right, so let's take a look. All right, so here's this chart. Now, for our course, you do not need to have this chart memorized. You just need to know how to read and interpret the chart. So if it were a MCQ or FRQ problem, they would give you the rotational inertia for different objects. So you are never required to memorize the rotational inertia formula. The only thing that you need to know is that rotational inertia is mr and squared. So if we're like thinking in like problem solving strategy, there's a high chance that this squared here matters, right? So they love problems where they're looking at, if you're changing the radius by this amount, how much would that change your rotational inertia? Okay, so back to this chart. So if we are looking at this chart, right, I'm going to just choose two different objects here. Let's choose the solid sphere versus the thin spherical shell. So a solid sphere is just like what it sounds. Let's say it is a solid sphere, I don't know, like a bowling ball. Okay, bowling ball. And a thin spherical shell, this is like a ping pong ball. Ping pong ball. All right. So one is hollow and one is solid. So according to this chart, right? So hopefully you're seeing that each one of these has mr squared, mr squared, mr squared, right? This is ml squared, but that's basically r squared. So they all have this mr squared. But the thing that separates each of these situations is the constant that's in front of it. So here we have a 1/2. Here we have a 2/5. There's a 1 here, a 12th, a third. All right. So if I were to ask you which so let's say we have two objects. We have a solid sphere and a thin spherical shell, but the m is the same and the r is the same. Okay, which one has more rotational inertia? So what you're actually looking at is this numerical constant that's in front of it. So if you have two objects, same mass, same radius, that's rolling towards you, okay, it would be harder to stop the thin spherical shell because 2/3 or 0.667 repeated is greater than this 2/5, which is 0.4. So this has a greater rotational inertia than this solid sphere. Okay, now let's try a different example here. So what about this? Let's say we have a cylinder and a hoop. So essentially two cylindrical objects, right? But one is just, so when we say a cylinder, this middle inner part is filled in, and that's the main focus here, versus the hoop where the inside is empty. So the idea for these two situations is that the rotational inertia for this solid disk is going to be less than the one with the hoop. And it's because of the way that this m and this r squared are, I guess, like the relationship between it. Okay, so the whole idea behind this is rotational inertia. And so when these two objects are spinning, when we're looking at the rotational inertia, the mass that is spinning is the important thing. So for this hoop, the mass that is spinning, right? If the m and the r are the same for both situations, the mass is collected. It's denser at location r. Before situation like here on the solid disk, right? It has the same amount of mass, but this mass is distributed. So if we were to take a look at the outermost part, like we did with the hoop, because the mass is distributed, the mass at the same point r is less than the mass over here. Because here, the mass is densely collected versus the mass here, which is not densely collected. It's just spread or distributed evenly. All right. And the very last thing I want to go into is rotational inertia for multiple objects. So one thing that you're required to do is if you are given a situation where they don't give you the I, for that specific situation, you are expected to figure out the rotational inertia. So let's say we have 2 points, and these 2 points are along this horizontal axis, right? And you know what? For the sake of not using our imagination too much, let's say they're connected by a rod, right? But here's the important thing: the rod is massless, meaning that even though the rod's rotating, because there's no m, it does not have a rotational inertia. All right, and let's say it's rotating right along the middle there, so it's like spinning, let's say this way and this way, kind of like the baton. So if you have a rotational inertia like this, the idea is I is a summation of all the rotational inertias. So if we're going to call this I1 and we're going to call this I2, the formula would just be I1 plus I2, meaning that because this is a point particle, it will be mr squared plus mr squared, and you will put like subscript 1, 1, 2, and 2. And those different subscripts will tell you the different variables to put in there. Okay, so you could just come up with the rotational inertia for that situation. All right, what about one rod about the center and one rod and 1 point? So same thing as before, except now this rod does have mass, and we're going to put a point right there. So we know that the rotational inertia for this point would be mr squared, but what about the rod? And so for a AP problem, they would tell you that the rod about the center would have a rotational inertia of 1/12 ml squared. Okay, so here the I would be a 12th ml squared, and so the summation would just be a combination of these two. All right, the same idea of this one here, same situation as before, except now we're just putting two particles on either end, and you're going to be rotating it about the center, and it'll be a summation of particle 1, particle 2, and of course the rod would be the last rotational inertia. All right, I'll see you next time. Bye bye.